Okay, welcome to Chapter 4's lecture. So I'm just going to record this lecture just to kind of keep us on pace since we had the holiday and everything like that. It's not a very long chapter. This way you can review it and watch it at your convenience here before exam one. This will be the last chapter that will be on exam one. Um, but again, just to try to keep us on pace so we don't fall too behind with the holiday and stuff that we have, I'm just going to kind of record this lecture. And as always, if you have any questions, you should definitely ask during discussion time or anything like that. I'd be happy to go over anything during that time. So chapter 4 is about energy. So we're going to talk a little bit about energy and ways that molecules sort of interact with each other. So let's first talk a little bit about energy. Energy really is the capacity to do work, and there's different types of energy. There's potential energy, which is sometimes referred to as sort of stored energy. And then there's kinetic energy, which is that energy of motion. So the classic example, of something that's sort of potential energy, that classic big boulder on the hill there has a certain amount of potential energy or stored energy, really just based on its position. So kind of based on its position, it has a certain amount of energy associated with it. Now, when we talk about energy, there's the law of conservation of energy, which means that energy cannot be destroyed nor created, but we definitely can transform energy from one form to the next. And that could happen with the other classic example when the boulder actually goes over the fence or the hill. It obviously gets transferred from potential energy to kinetic energy, which is the energy known as movement. And obviously, it has a certain amount of kinetic energy until it hits the floor, if you will. And when it hits the floor, hopefully nobody's underneath there, but when it hits the floor, it will transfer all that energy to, say, the floor or whatever's underneath there. The boulder will come to rest at a lower potential energy than it started with. And again, that energy, even as it hits, will be transferred to, again, the floor in this case, as it hits that. There's thermal energy. There's energy stored within bonds. So when we have a bond, in order to break the bond, energy has to be put in. And when it does, it gains enough energy to sort of wiggle apart. When we want to make a bond and guys are sort of away from each other and they're wiggling around, they need to lose a certain amount of energy to allow them to sort of come together to make that bond. And in terms of energy, there's really sort of two processes which we oftentimes come across. One is a exothermic process. And exothermic means that heat and energy is released. And endothermic is the process where we talk about heat and energy being absorbed. So in the process, for example, of the bond being broken, energy needs to be put in, which are absorbed by the bond, and that's endothermic, helps them break apart. In the case of them, when they're kind of wiggling around, they need to lose energy, which is exothermic, and again, allows them to slow down and sort of make that bond. When we do talk about energy, there's certain units that are very common, and a calorie is a very common unit, and a calorie with a lowercase c is the amount of energy that's needed to raise the temperature of 1 gram of water by 1 degree Celsius. And a joule, which is also a very common unit of energy, is the energy unit associated in chemistry a lot that we use. And the relationship between those two things is 1 calorie is 4.184 joules. Other common units are kilojoules and kilocalories. 1 kilojoule is 1,000 joules, so that's that kilo relationship. Same thing here, 1 kilocalorie is 1,000 calories as well. Now, these lowercase calories shouldn't be confused with a capital calorie, and the capital C calorie is more of a nutritional calorie. So 1 capital calorie is actually 1,000 of the lowercase c's, and that's equal to 1 kilocalorie. So a capital C calorie or nutritional calorie, again, is 1,000 of the little calories. We usually see that, for example, in nutrition, or if you're on the treadmill, it says how many calories that you burnt, or some treadmills sometimes used to say how many kilocalories that you burnt. again, because those are equal to each other. So in chemistry, usually little case calories is what we look at, and that is the difference between those two things. As I just saw here, I kind of jumped the gun there, but the amount stored energy in a nutritional calorie, again, uppercase C or capital C. And when we talk about sort of nutritional calories, there are certain things that have caloric value. And the three major types of things that have caloric values are protein, carbohydrates, and fat. And for example, this is how we get like on a nutritional label. So if you look on a food item, for example, on the nutritional label, there'll be a whole bunch of information, but somewhere they'll tell you how many grams of protein there is in the food item, how many grams of carbs are there, how many grams of fat are there. And you can use these caloric values, protein and carbohydrates being 4 kilocalories. So this is basically 4 kilocalories per gram for each of these is the caloric value. And again, a capital calorie and a kilocalorie are the same. So that's why these look the same. And a fat is 9 kilocalories per gram. And you can use these labels here to, figure out how many calories a food item has. So for example, if you go back and find something to write with right there, that'll work. So for example, if you had a label where it said that there was 10 grams of protein, 2 grams of carbs in your food item, and let's just go with 4 grams of fat. And again, if you look on that nutritional label for those things, you can find those. And if you want to basically figure out how many calories that object has, and you didn't want to look at the actual label where it probably says that, you could actually calculate it. And you would calculate it by doing this calculation. You would go, okay, there's 10 grams of protein. Protein's caloric value, as we just saw from that table, is 4 kilocalories per gram. You also had 2 grams of carbs, and carbs are 4 kilocalories per gram. And we also had 4 grams of fat, and fat is 9 kilocalories per gram. So this would give you 40 kilocalories. 2 times 4 is 8 kilocalories. And our fat is 4 times 9, which would be 36 kilocalories. And if you add all that up, I'm going to grab my calculator just to make sure. 8 plus 36. Looks like 84 kilocalories if you added that all together. And probably your nutritional label would say this food item has 84 calories. Probably in my experience, it probably would say it has 80 calories. For some reason, a lot of times they like to round down on nutritional calorie labels for probably the obvious reasons. But sometimes you get the actual number, but sometimes they will round down. So again, you can look at each of these items and figure out its caloric value and actually calculate it. So let's talk about the 3 states of matter that we've talked about previously in this class, and that is solid, liquid, and gas. And remember that, when we do have solid, everybody is typically in there pretty tight to each other. When we have liquid, there's a little bit more room for movement, still relatively tight to each other. And when we get into the gas phase, everybody's completely broken apart from each other, really flying around. So in terms of energy, solid usually doesn't have a lot of energy, right? Because there's not a lot of movement going on. Liquid, there's a little bit more energy. Again, in liquid, the molecules or atoms have enough energy basically to pass each other. In the gas, they have a lot of energy as they are flying around in this container. Otherwise, they wouldn't be in the gas state. And they do need a lot of energy just to break apart from each other. And some of the properties that we've talked about before in terms of these things, gases, they fill the container uniformly as they are flying around. Liquid, they have a fixed volume, but they do take the shape of the container. So again, if you took some liquid water and put it in a water bottle, or you took that water bottle liquid out of there and put it into a trash can, it would take the shape of the trash can. So they do have a fixed volume, which means if you had 10 milliliters and we're not a klutz, you should still have 10 milliliters when it's all said and done. Just may look different in a different container. Solid guys have a fixed shape and volume, very hard to change. So like the desktop, very hard to change the size of it and stuff like that. Now, when we do go from, say, solid to liquid to gas, we also talked about some transitions. As you go from solid to liquid, again, that is the process of melting. As you go from liquid to solid, that's the process of freezing. Going from liquid to gas, that is evaporation or vaporization. Going from gas back to liquid, that is condensation. Going from solid, where we skip the liquid part and directly to gas, that is sublimation. And going the opposite way, gas, skipping liquid, back to solid. I'll write it over here. That is deposition. Now, in terms of energy, as we also, I think, talked about earlier on in the semester, as you go from solid to liquid to gas, that's an endothermic process. You need to put heat and energy in. So if you had like an ice cube and it picks up heat and energy, it starts to melt the liquid water. Liquid water, if you put it on the stove and start heating it, it will go from liquid water to steam. Opposite is true as we go from gas to liquid to solid. That's an exothermic process where heat and energy is released. So let's say you had water molecules flying around in steam. As they lose energy, they slow down, and as they come to each other, they no longer have enough energy to escape each other. So they kind of stick and they go into the liquid phase. And then if you continuously remove energy, those liquid molecules no longer have enough energy to pass each other and they get into that solid state. So endothermic going solid liquid to gas, exothermic going the opposite way around, going from gas to liquid to solid. A reminder as well, when we talk about melting and freezing, it does occur at the same temperature as we talked about before, I believe. So this occurs at the same temperature. And that's the normal freezing point or melting point for a substance. So for example, for water, that's 0 degrees Celsius for water. And evaporation and condensation also happens at the same temp. And again, for water, that's 100 degrees Celsius. If you're not talking about water, it's going to be different numbers. It just depends on 100 degrees Celsius, what's going on. If you continue to put energy in there at 100 degrees Celsius, you will go into gas. If you remove energy for water at 100 degrees Celsius, you'll go into liquid water. Really directly at those temperatures, for water, for example, at 0 degrees Celsius, you have a combination of solid and liquid happening at equilibrium. It's not until you get above 0 degrees that you get liquid water, not until below 0 degrees that you get ice. And same thing at 100 degrees Celsius, you got liquid and gas sort of in equilibrium with each other. Not until you're above 100 degrees that you really do get gas, not until you're below 100 degrees that you get liquid water. So exactly at the melting point, freezing point, boiling point, you have both of the phases in equilibrium with each other. So we're going to talk about different types of intermolecular forces that hold molecules together. And there's two types of forces. There is ones that are referred to as intramolecular force and intermolecular force. Intramolecular force means within the molecule. So if you took just one water molecule, it is the force between the oxygen and hydrogen, those sharing of electrons that hold it together on each side. Now, intermolecular force is when you take, say, 2 water molecules, 3 water molecules, however many. And it is the force that holds this one water molecule together with another. So this is the force that holds 2 or more molecules together. So intramolecular force within one molecule, everything that holds it together, and intermolecular forces are the forces that hold one molecule together with another. So, for example, when we do have water, water is a polar molecule, which means the negative side of water, which is the oxygen, is attracted to the positive side of water, which is the hydrogen. And it's that bond right there that holds it together. And that's an intermolecular force, would be this guy. Now, an intermolecular force is always weaker than an intramolecular force. This is a very strong force. And if you just think about water itself, that is what happens when you heat water. When you heat water, because the intermolecular force is weaker than the intramolecular force, when you start to heat water, the first bond that breaks is actually right here between 2 water molecules. And you end up with 1 water molecule, 2 water molecules. Now, if the opposite was true, and the intramolecular force, the force within each individual molecule, was weaker than the intermolecular force, when you would start heating water, every individual water molecule would start to break apart. And you would get a ton of hydrogen gas and oxygen gas being formed. And if you ever heated water, you know that doesn't happen. Otherwise, you probably would never get to the pasta part of making dinner there, because you do not generate hydrogen gas or oxygen gas by heating it, because that force between the oxygen and hydrogen is super strong compared to the force between 2 water molecules. So intramolecular forces, which are really like ionic bonding, are covalent bonding. Those guys are always going to be stronger than the strongest intermolecular force, which can be one of these 3 things we'll talk about: London dispersion forces, dipole-dipole, or hydrogen bonding. The stronger the intermolecular force, as we'll talk about, affects things like melting points, boiling points. So the stronger this force, for example, between 2 water molecules is, the stronger that is, the harder it's going to be to break it apart. And what that would mean is it should end up having a higher boiling point, for example, which is the part where it should break apart. The weaker the intermolecular force, the lower the boiling point will be, because it's not going to be holding those 2 molecules together super tight. So let's start with dispersion forces. And dispersion forces are relatively weak interactions that occur based on a temporary charge of the molecule. These are typically the ones that result from when we have nonpolar molecules together with nonpolar molecules. So this is typically our nonpolar interaction. Remember that basically nonpolar means equal sharing of electrons. In a molecule as a whole. So the entire molecule has an equal sharing of electrons. What that essentially means is when you have a nonpolar molecule, NP for nonpolar, it is essentially neutral, if you will. It has no charge, has no positive side or negative side. So what happens though is, and in some cases, when you have a nonpolar molecule next to another nonpolar molecule, the electrons, for example, in this first nonpolar molecule may all decide, hey, let's just go this way. And if that occurs, what happens in the first nonpolar molecule is it temporarily gets a charge. And because it now temporarily has a charge, because all the electrons decide to go to the left-hand side in this example, the electrons in the second molecule is going to go, I want to be near the positive guy. So the electrons in the second molecule is going to go to the left. And now the second molecule, which did not have a charge to begin with, will now gain a temporary charge. And ultimately what we get is the basic type of attraction that occurs for intermolecular forces, which is the positive negative attraction between two molecules. So the positive side in one will be attracted to the negative side in the other. And now they temporarily have a way to interact with each other. This type of bonding is really, and most people just call it dispersion forces. So dispersion forces are these really temporarily made attractions that occur. One way it could happen is the electrons in one molecule decide to go one way, electrons in the other decide to go towards it, and you get this attraction. It's weak because as soon as the electrons decide I'm going to come back the other way, it's going to kind of break apart and new ones will form. Those will break apart and new ones will form. So the attraction here is a relatively weak attraction because it's temporary. A temporary dipole is what we saw when we talk about bonding, those arrows where there's a negative side and a positive side. And if you have a polar molecule, it will have a positive side and negative side that occurs. But these are really weak type forces because as soon as those electrons go back the other way, it will then kind of break apart and happen again. Also means, though, if you're comparing two nonpolar molecules, the one that is larger will have a stronger attraction. And that is because if you have a larger molecule, which has more atoms and more elements involved, or atoms of the elements, that means more atoms means you have more electrons. More electrons means you have a greater chance that these electrons will start to move around and a greater chance that this interaction will occur. And that's why when we compare, say, something like CH4, which is nonpolar, to something like C8H10, this guy here, they both will use dispersion forces because they're both carbon and hydrogens. They're both nonpolar molecules. So the best that they can do is dispersion forces here. But because this guy here, the C8H10, has more atoms, more electrons, there's a greater chance that he can get that temporary charge to occur, and it will be stronger than CH4, which would also use dispersion forces. So here's a prettier picture than what I drew, but again, this guy that normally does not have a charge temporarily gains a charge. Same thing with the guy on the right as the guy on the left. And now that they temporarily gain a charge, they have a way to interact with each other and kind of hold that together. So again, dispersion forces, relatively weak type of intermolecular force. And typically this is the main intermolecular force for nonpolar molecules interacting with other nonpolar molecules. The next type of interaction is a dipole-dipole. And remember that if you have a dipole, you pretty much have a polar molecule. So this is the force that holds one polar molecule together with another. And if you have a polar molecule, if you remember, what a polar molecule means is that there is a side that's partially positive, there's a side that's partially negative, right? Kind of that arrow pointing in this direction. And you would have another polar molecule that has a positive side and a negative side. And it is that positive side of one and the negative side of the other that gives it a way to interact with each other. And this interaction is our dipole-dipole interaction. And it is typically what happens between two polar molecules. So for example, here's formaldehyde. And if you go through sort of the molecular polarity of formaldehyde, The side by the carbon is more positive. The side by the oxygen is more negative. So when two formaldehydes, for example, get together, the negative side of one is attracted to the positive side of another, and now they have a very good way to interact with each other. So dipole-dipole is for two polar molecules that really do not have the ability to hydrogen bond, which we'll talk about next, but is the way two polar molecules basically interact with each other. You may ask the difference, what is the difference between this and dispersion forces? The difference between these two is if you have a polar molecule, it has a fixed side that's positive and negative. No matter what the situation is, a polar molecule will always move around with a positive side and a negative side. And that is different than what we were talking about here with our dispersion forces. In dispersion forces, most of the time, our nonpolar molecule has no charge. So it only gains a temporary charge of that positive and negative guy. So it is not moving around 100% of the time with this fixed positive negative charge. It is affected by things with charge. It's affected by electrons that move around. The difference is with our polar molecule, it is always moving around with a positive side and negative side. It is not affected by anything else that may be near it. It will always have that positive side and it will always have that negative side that is there. So that's why that is the difference between those two. Even though they're both doing positive, negative, polar guys have a fixed positive charge no matter the situation, which means they're good to go. They're ready to interact with that positive, negative attraction. Our dispersion forces and our non-polar guys are most of the time traveling around with no charge, which means they need something to happen to them to get them in a place where they can interact. So for that reason, dipole-dipole is much stronger than dispersion forces. So if you have something that has the ability to do dipole-dipole interactions, it should be much stronger interaction than somebody that can only do dispersion forces. Also means things that can do dipole-dipole should have higher boiling points, melting points, and those type of situations because of that. Now, the last type of intermolecular force is hydrogen bonding, and it actually is a type of dipole-dipole interaction. It's a very strong type of dipole-dipole interaction, and it is a bond between hydrogen and oxygen, nitrogen, or fluorine. And if you look on the periodic table, electronegativity increases this way. And because it does, what that means is when you have hydrogen bonded to fluorine, hydrogen to oxygen, hydrogen to nitrogen, there's a big difference in electronegativity between those two. And that's going to create the hydrogen side being more positive, the fluorine oxygen side or nitrogen side being more negative in that bond. And it has a way to interact with each other. So water is a very good example here. Our oxygen, which is here, is partially negative. Our hydrogen, which is here, is partially positive. It has a way to interact with each other. So you may ask yourself, what is the difference between hydrogen bonding and dipole-dipole? There is no real difference other than hydrogen bonding is a type of dipole-dipole, and it is the strongest out of all three of those intermolecular forces. But it does need to be a hydrogen that has the ability to hydrogen bond. So earlier we talked about CH4, which is methane. Now methane's got a ton of hydrogens, but it is not a hydrogen bound to an oxygen, nitrogen, or fluorine. And if you remember from bonding, the carbon-hydrogen bond in terms of electronegativity, 2.5, 2.1 in terms of those values, the difference is 0.4, which means it's a non-polar bond. So although CH4 has a ton of hydrogens, not one of them can do hydrogen bonding because, again, there's no hydrogen, nitrogen, oxygen, fluorine together. So even though it does have those hydrogens, cannot hydrogen bond, it does need to stick to dispersion forces, as we talked about earlier. So again, just because you see a hydrogen doesn't necessarily mean that it will have the ability to hydrogen bond. Typically needs to be a polar hydrogen. And again, these three elements need to be involved, bonded directly to the hydrogen in order for that to happen. So here in DNA, we have some hydrogen bonding between an oxygen, hydrogen in one base, nitrogen and hydrogen happening here in another base. Again, relatively very strong type of interaction. So here's sort of a slide that summarizes them in terms of the strongest intermolecular force. It is hydrogen bonding. And that is basically your polar molecules that have the ability to hydrogen bond. In the middle, and really strong as well, but not as strong as hydrogen bonding, is dipole-dipole. Also for polar molecules with no ability to hydrogen bond. And the weakest out of all of those is our dispersion forces. Again, here, that is typically your nonpolar guy in nonpolar interactions. So strongest is hydrogen bonding, next strongest dipole-dipole, and the weakest by far is our dispersion forces. So for example, if I had something like this is a polar molecule. Again, having that fluorine there can make the overall molecule polar. Does not have the ability to hydrogen bond, even though, again, all these are hydrogens. These are nonpolar, these bonds between carbon and hydrogen. So it would use dipole-dipole. Again, does not have the ability to hydrogen bond, would be its strongest source. If we took something like this guy is going to have the OH group. That's a hydrogen bound to an oxygen. That's going to be more negative. That's going to be more positive. This guy has the ability to hydrogen bond in that case through here. So something else that has maybe an OH group, the negative side of one would be attracted to the positive side of another. So it would be hydrogen bonding. So if you had something like N2, for example, N2 is two nitrogens together. That is going to be nonpolar, which means it needs to use dispersion forces. So strongest out of all three, hydrogen bonding for polar molecules that have the ability to hydrogen bond. Dipole-dipole, next strongest for polar molecules without the ability to hydrogen bond. And the weakest by far of all three is dispersion forces for things that are nonpolar. And the only thing with our dispersion forces, as we talked about, the strength of it increases as the size of the molecule gets larger. So the bigger the nonpolar molecule, the stronger its dispersion forces will be. All right. So let's talk a little bit about some of these things that we kind of touched upon earlier. The boiling point is the temperature at which basically we go from liquid to gas. So that again is that transition as we talked about, going from liquid to gas, which is known as boiling point. Obviously, the stronger the intermolecular force, the higher the boiling point would be. The weaker the intermolecular force, the lower the boiling point would be. The melting point is that thing that we talked about where transition, where it goes from solid to liquid. Same idea here. The stronger the intermolecular force that's holding those molecules together, the higher the melting point would be. Again, you got to put more energy in there to break them apart. And same idea with our boiling point. The higher it would be because you have to put more energy in there. So if I had something that had the ability to hydrogen bond, It should definitely have a much higher boiling point, melting point than something on the other end of the spectrum, something that is dispersion forces, we should have a much lower boiling point and melting point. Again, the weaker that interaction is between two atoms, the weaker that bond is between two molecules, excuse me, the less energy you has to put in there to break them apart, less energy to put in there to break them apart, the lower the boiling point or melting point temperature would be, and vice versa. If this bond or intermolecular force between these two molecules are really, really strong, you got to put more energy in there to break them apart. The more energy in there that you put to break them apart is going to result in a much higher boiling point and melting point than we would expect from something with a lower one. And that's what we see here in this slide. This is our nonpolar CH4, going to be stuck with our dispersion forces as opposed to our water, as we talked about, which can do some hydrogen bonding between the negative and the positive guy here. And that's a very strong force. So again, we see higher melting and boiling points here than we do over here because of the ability of the hydrogen to, or water to hydrogen bond. These are two nonpolar guys. So what makes these nonpolar for the most part? They're all carbons and hydrogens. So pretty safe bet if that's all you got going on here. They're both nonpolar. But in comparison, even though they're both carbons and hydrogens, the guy on the right, butane, is a much larger molecule. So again, the larger the molecule, the more chance of electrons, because there's more electrons, to really be able to kind of move around and create those temporary attractions. And it also gives them more places for those attractions to occur. And that results in a much stronger attraction. So in terms of boiling points and melting points, we would choose butane as having the higher ones because it's a much longer molecule. Even though they're both basically using the weakest type of intermolecular force, the butane will be stronger in terms of the weaker force because it has those more electrons and a greater chance of those attractions occurring. Okay, we're going to then talk about specific heat here just a little bit. We're not going to do any calculations involving specific heat. So if there's calculations in the chapter, we're not going to really do any calculations involved. We're just going to talk about what it is a little bit. And like I said, really no calculations involved in this particular one. So the specific heat is the amount of heat or energy that's required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So specific heat are sometimes referred to as specific heat capacity. Has units of joules per gram per degree Celsius or calories per gram per degree Celsius. And basically what that means is the definition is the energy in joules required to raise 1 gram of a substance by 1 degree Celsius. So that's why it has all those units. The larger the specific heat value, the more energy is required to change the temperature of a substance by 1 degree Celsius. Liquid water has a specific heat capacity of 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. That's a relatively high specific heat capacity. That means in order to change 1 gram of water by just 1 degree Celsius, you got to throw in there 4.184 joules per gram per degree Celsius. That means if you have something that has specific heat capacity of 0.4 joules per gram per degree Celsius, you need to put in only 0.4 joules of energy to raise that same gram of a substance by 1 degree Celsius. It's almost a 10-fold decrease in the amount of energy required in those two examples there. And again, so the larger the value for specific heat capacity, the more energy that's required to change that substance temperature by 1 degree Celsius. Here's a table from your book. It's on specific heat capacities in both units. So you can see something like aluminum, you only need to put in there 0.214 joules to change every gram by 1 degree Celsius. And that's very different than, as you can see, water, which is 1 calorie per gram per degree Celsius, or 4.184 joules. I think I misspoke there. That's 0.214 calories that you need to change the temperature. So larger specific heat capacity, more energy required to change the temperature of that substance by 1 degree Celsius. That's why technically, excuse me, that's why technically water has a very high specific heat capacity. And that's also why people get concerned when we talk about water changing overall its temperature in the world here by just a little bit of degrees Celsius or whatever. Sometimes you may look at it and go, it only changed just a little bit, right? But if you think about how much energy is required just to do that little bit of change for how much water there is in the world, that takes a tremendous amount of energy to do that, just a little bit of change. Hence the idea of global warming and stuff like that, right? So even though it may seem like, the overall temperature only went up by maybe like, half a degree or 1 degree overall, it still takes a tremendous amount of energy to raise it, which is the idea behind, obviously in order to do that, change that amount of water by that 1 degree Celsius, it must require a certain amount of energy to do that. And, that's the concern, obviously, with global warming and stuff like that. When we do talk about energy and phase changes, we talked a little bit about this earlier. So just to kind of finish out officially here talking about it, when energy is absorbed, as I talked about, it's said to be endothermic. So again, heat and energy being absorbed. And as we talked about phase changes, that's what happens when we go from solid to liquid to gas. Again, we're putting energy in to do that, and that is endothermic. And that is the opposite as we go from gas to liquid to solid. We are removing energy or releasing energy. And that is endothermic in that case. And when we do a phase change is just simply a substance going from one phase to the next, either being the phases being solid, liquid, or gas. And that is, again, a reminder, a physical change, right? So even though we talk about ice going to liquid water, going to steam, and that is our solid, our liquid, and our gas, this is all still fundamentally in all three of those spots. It is still fundamentally still water. So phase changes are just physical type changes. We're not fundamentally changing any substance into anything new. So converting a solid to a liquid, as we talked about, is called melting. And again, endothermic, it needs to absorb that heat and energy. So if you take an ice cube out, for example, of the freezer, it's going to pick up all that heat and energy from the surrounding air, and it's going to start to melt. Obviously, if you want to put it back together, you could. You could take that liquid water and put it back in the freezer, and it will become ice. So when you put the liquid water in, you're removing energy into the freezer, and that's exothermic, right? As the energy is being released. And it's going to allow those water molecules now to basically slow down and essentially no longer could pass each other and get into ice in solid one. Water is unusual, right? Water, because of its hydrogen bonding, is less dense than liquid water, which is unusual sort of property of substances. Usually in their solid state, they're more dense than their liquid state, but water is an exception. And that's because when water molecules come together through hydrogen bonding, let's draw it this way. As they sort of hydrogen bond to each other, it creates this really wide open space between different water molecules. So they really can't get in tight to each other, which is also a very unusual sort of property. Usually, it takes when things go solid, it's like packed in there pretty tight to each other, not a lot of room. But water is unusual in that case. And that's, again, why our ice cubes, for example, float, right, in our soda or whatever we put it in, because it's actually less dense than liquid water. Again, a very unusual sort of property. Now, when we do change something from solid to liquid or liquid to solid, this occurs again at its normal melting point or freezing point. And it all happens at the same temperature. So again, for the example of water, this all happens at 0 degrees Celsius. And at 0 degrees Celsius for water, there's a certain amount of energy required to do nothing more than take the water in the solid state to water in the liquid state and backwards. Not changing its temperature, not taking it from 0 degrees Celsius to 20 degrees or 0 degrees to -4 degrees. Right dead on at 0 degrees Celsius as you do that transition going from solid to liquid. There's a certain amount of energy required just to do that, and that is what is known as the heat of fusion. The heat of fusion is sometimes referred to as delta H of fusion. Delta H is what is known as the enthalpy. We're not going to talk too much about that. Enthalpy is the heat of a reaction, but there's a certain amount of energy required just to simply do that process at 0 degrees ice to take it from 0 degrees ice to 0 degrees liquid water. And that's the heat of fusion. It's 79.7 calories, which roughly, if you kind of do that conversion there, is somewhere around 333 joules per gram is the specific heat capacity or the heat of fusion for water in joules. So that means for every gram of water, you need to put in there 333 joules of energy in order to do just simply take it from ice to liquid water. Again, we're not going to do any calculations with it, but that is what the heat of fusion is. Now, the vaporization and evaporation is the process. Is the process as we go from liquid to gas or gas back to liquid. Again, this happens as we talked about at our boiling point, our normal boiling point. And again, occurs at the same temperature for liquid water. Again, we're talking 100 degrees Celsius, specifically for water. And it's that point where it gains enough energy to break apart from each other in the liquid phase completely into the gas phase and fly around free from each other as gas molecules. That again is endothermic. As we go from liquid to gas, energy needs to be put in. And exothermic as we go the opposite way, which is known as condensation, as we talked about earlier, when we go from gas back to liquid. There is also a certain amount of energy required to do just that transition, just like we were talking about with solid to liquid. Going from liquid to gas or gas back to liquid, there's a certain amount of energy that occurs. And again, for water, at 100 degrees Celsius is where this occurs, going from gas to liquid or liquid to gas. And that is what's known as the heat of vaporization. The heat of vaporization are sometimes referred to as the delta H of vaporization, which delta H again is the enthalpy of vaporization, but people usually just call it the heat of vaporization. And roughly speaking, it takes about 2260 joules per gram is the heat of vaporization for water. Now, if you compare the two numbers, the heat of vaporization for water is 2260. The heat of fusion for water was 333 joules per gram. And that again is going from solid to liquid or liquid back to solid. You can see just from the numbers that it takes almost 7 times the amount of energy to go from liquid to gas as it does to go from solid to liquid. And that is because if you think about the states, going from solid, everybody's packed in pretty tight to each other, to liquid, where they're still packed in pretty tight to each other, a little bit more room for movement. But when you go from liquid, where they're packed in pretty tight to each other, to gas, where they have completely broken apart from each other and flying around, it takes a tremendous amount of energy, more energy to do that transition, liquid to gas, than it does to go from solid to liquid, because you need more energy to get everybody to completely break apart from each other. So that's always something that's true for all substances. That transition going from liquid to gas always takes more energy than the transition of going from solid to liquid. And again, it's just simply the idea that we need to break everybody apart. So what's happening here is all these water molecules are being held together by hydrogen bonding. we need a lot of energy to be put in there to get them to kind of break apart from each other and fly around. Again, in the case of going from solid to liquid, we need a little bit of energy because we're not really completely separating everybody. They're just kind of breaking apart from each other a little bit more than they would as they go from liquid to gas. And our sublimation and deposition, as we talked about, going from solid directly to gas, we skip liquid here. And same idea going backwards, gas back to solid, skipping liquid. Sublimation is that process solid to gas. And it is endothermic. Again, need to put energy in there to break everybody apart, go directly from solid to gas. Dry ice is an example of that. Dry ice is actually CO2. So if you've ever seen dry ice, it goes directly from solid to gone. No liquid cleanup in between. It goes directly, under normal conditions, from solid state to gas state. Deposition is the opposite, going from gas back to solid. Again, skipping liquid here. That is exothermic. So again, we have gas molecules flying around fast and furious. You need to release the energy. Exothermic, they slow down, and all of a sudden they clump together into the solid state to do that. So as you can see here, this is dry ice, which is CO2. And if you've ever done it, like I said, we, under normal conditions, actually go directly from solid to gas, no liquid in between. In order to get the liquid to actually happen, you need an extraordinary amount of pressure that doesn't occur under normal situations to get it to actually go into the liquid state. It won't happen under normal conditions. And that's what we see here. This is what is sometimes referred to as a heating curve. So for example, if this was ice, this was liquid water, and this was steam, and this is all water, this would be right here, 0 degrees Celsius. This right here would be 100 degrees Celsius. And in this case, we would be going from ice, which is solid, to liquid water, to gas up here. So this is what I was talking about at the transition, right here between B and C. That is our normal melting point, freezing point, and that is where we would use the heat of fusion to do that. Again, it's not until you get a little bit above 0 that you have liquid water, not until you get a little bit below 0 that you have true ice. Right there, dead on 0 degrees, you have basically both things happening, ice and liquid water together, kind of like ice crystals, sort of happening at that point. Same thing here between D and E is plateaued flat, and that is where we would use something like the delta H of vaporization. Same idea here, at exactly 100 degrees, you have both liquid and gas happening together at the same time. Not until you get above 100 degrees that you actually get gas, not until you get a little bit below 100 degrees that you really do get liquid water. But again, right on 100 degrees is the normal boiling point at that point. And you have both guys in both phases. And this is a cooling curve, which is essentially the same thing. It's just going the opposite way around. So, whoops. This again up here in this case would be like our steam. This would be our liquid water. And this would be like our ice here. So again, this would be 0 degrees Celsius. This right here would be our 100 degrees Celsius. Same idea. This is all going from gas and liquid to solid. This is all exothermic processes happening. Heat and energy released. As opposed to the first curve that we saw there, this is all endothermic processes. Heat and energy absorbed. Okay, so that actually does wrap up chapter 4. Again, a reminder that there are some calculations and stuff about specific heat and things of that nature. We're not going to do any specific heat calculations. You just need to know what specific heat is in relationship to Higher specific heat capacity, more energy required to change the temperature. Lower specific heat capacity, less energy required to change it. You need to know the three types of intermolecular forces: hydrogen bonding, which is the strongest between polar molecules that have the ability to hydrogen bond. Dipole-dipole interaction, also strong but weaker than hydrogen bonding for polar molecules without the ability to hydrogen bond. Dispersion forces for nonpolar molecules, that is the weakest of all three, usually for our nonpolar. And you need to know the different phases we talked about: solid, liquid, gas. You need to know the transitions, what they're called: condensation, evaporation, melting, freezing. Um, and you also need to know, again, which processes are endothermic, which is absorbing energy, which processes are exothermic, releasing energy. And obviously, just a little bit about energy in terms of units, common units, joules and calories, and a little bit about the nutritional calorie we talked about at the beginning. Other than that, that should wrap chapter 4. Thank you very much for listening to it. Again, please, we're not going to officially lecture on this in class. This will serve as the lecture to kind of help keep us on track. And again, this will be part of exam 1. If you do have any questions after reviewing this, please feel free to contact me, email me, or during discussion, you're more than welcome to ask questions. Other than that, I will see you live at some point, either Monday or Wednesday, depending on when you watch this, I suppose. So either have a good rest of your day, good night, good morning, or a good weekend, I suppose, depending on the day that you're watching. Other than that, I will see you next time.